Hey everybody, it's titration time. It's the time where we are going to find out the unknown solution using titration, which is a method of adding an acid to a base or a base to an acid and determining the concentration of an unknown acid or unknown base. To do this, we're going to first of all think about why we would want to do a titration. Well, one reason why is if we added different things together. Here, if we added hydrochloric acid and sodium hydroxide together, which of these would be least toxic? So think about which one of these you think would be least toxic and why. And then are the final solutions acidic, basic, or neutral? So if we look at these three solutions here, after we think about our answer, these three solutions are not all the same. You can see in each solution you're adding 100 milliliters of the hydrochloric acid. So here if we look at the solutions here, we've got sodium hydroxide and hydrochloric acid. Out of the three of them, which one do you think is the safest? And most people would say, it looks like the middle one. This one's the safest. Well, why is that? Well, you have an acid, you add it to base, and it's a neutral solution. Top one here, you've got the acid, which gives up the H+, the base, which has the OH-, and when you add those together, you got double the acid than the base, so you're going to be left over with an acidic solution. And then down here, you've got a basic solution. So if you had to drink one of these, this one would probably be the best. Although, what would it be if you added NaOH and HCl together, sodium hydroxide and HCl, equal amounts of each? You would get NaCl, which is salt, aqueous, and you get HOH, these two here. And HOH is commonly written as water, H2O, and that's a liquid. So this here is an example of a neutralization reaction. In a neutralization reaction, you can calculate the amounts of the reactants and the products and see their ratio to see what product you should produce. So the chemical equation for a neutralization reaction shows the ratio in which the substances combine. So here's your hydrochloric acid and sodium hydroxide. These two combine here in a 1-to-1 ratio, making sodium chloride and water. This here is always water in a neutralization reaction, and this here is a salt in a standard strong acid, strong base neutralization reaction. A titration is a procedure in which the neutralization reaction is monitored with an indicator, allowing you to calculate the unknown concentration of an acid or a base. So tomorrow we're going to be using an unknown, in this case, we're going to be using an unknown substance and testing with another known substance and finding the concentration, or you can also find the volume if you know the concentration, which again you can usually do by measuring. So when the equivalent point is reached in titration between a strong acid and a strong base, the moles of the H+ and the OH are equal. So the moles of the H+ are equal the moles of the OH-. Okay? Now we know that molarity equals moles over liters. So moles equals molarity times liters. Now the cool thing is, if you look at the moles over here, that's the molarity times the liters equals the molarity times the liters of the OH. And when it's neutral, these two things are going to be equal to each other. Again, one can have a higher concentration and a smaller volume. One can have a smaller volume and a higher concentration, but they have to cancel out, so the moles are equal. This is called a titration. When you have a solution of a known concentration, and you gradually add that to an unknown concentration, when the chemical reaction is complete, that's usually the end point. This is called a titration. The equivalence point, though, is the point in which the reaction is complete. The indicator is the substance that changes color at or near the equivalence point. Okay? So that's the substance, that's like our universal indicator or our cabbage juice that we've used before. We're going to be using an indicator called phenolphthalein in this lab. So here you can see a titration setup. Here is our beaker. We're going to be using a 125 milliliter beaker here. And this object here that's long, this is called the Buret. Okay, you also need a distilled water wash bottle. And this here is the indicator. Indicator there. So you want to slowly add base to the unknown acid until the indicator changes color. So, key titration terms, things you need to know for the lab. First, a titrant is the solution of known concentration used in a titration. The analyte is the substance being analyzed, so that's your unknown. The equivalence point is when enough titrant has added to react exactly with the analyte. This is when a stoichiometric mixture is created, so exactly enough for it to be equivalent. The end point is different than the equivalence point. That is the point in the titration when the indicator changes color, so you know when to stop adding titrant. Now, in a good titration, these two will be close because you want to know where the end is. So if the indicator doesn't change color, but you're at the equivalence point, then the equivalence point and end point would be very different. You want them to be as close as possible for a accurate and precise titration. So, successful titrations. How do you be successful? The first is you have to have a reaction between the titrant and analyte must be known. So you must know hydrochloric acid and sodium hydroxide make sodium chloride and water. The reaction must be rapid. It must happen quickly. If it takes too long, then you may not be able to see the reaction when you add the titrant. Amounts must be known accurately, so you've got to measure precisely. And the endpoint must occur as close to actual as the equivalence point as possible. Again, endpoint and equivalence points are not the same thing, but you want to be close. So, here's how to titrate an acid with a base. This is using our indicator, phenolphthalein. Very fun word to learn how to spell. Now, in this figure here, we've got the acid in the bottom, and it starts clear. So here we have a clear, and it has an acid. Okay? And here we're adding the base. The base is again the titrant, and the acid in this case is the analyte. You add the base to the acid, and you swirl gently the beaker. Okay? If there's no color change, you can quickly add it. When you start to see a little bit of color change, you slow down, and then you slowly add drop by drop to reach the end point. You can also add a half of a drop as well by using your wash bottle to spray off the drop at the end, spray it off, and spray it inside and down the sides of the container. If your color is too dark, you've gone too far. Titration can be used in the analysis of acid-base reactions, which is what we're going to do in our class tomorrow in chemistry. So here is a sulfuric acid plus sodium hydroxide reaction. This reaction, you'll notice, is a little bit different. What's the ratio between the sulfuric acid and the sodium hydroxide? Here you've got 1 of these to 2 of these. It's a 1-to-2 ratio. So the ratio is a little bit different. You have to pay attention to that in the analysis. In AP Chem, we do what are called redox reactions. And this is an example of a redox reaction where you have, again, a solution here, a purple-colored solution, and it's changing the color here of this this analyte here. So this is iron and manganese. One is being oxidized, the other is being reduced. We'll learn more about that as we go on in the course about redox. Now, performing the calculations for acid-base reactions. So first you must list the initial species present and predict the reaction, write the balanced net ionic equation, calculate the moles of the reactants, and determine the limiting reactant. You want to calculate the moles required of each reactant or product. Convert to grams or volume as required. So here we have a question. We've got what volume of 1.40 molar sodium hydroxide is required to titrate 25 milliliters of 4.5 molar H2SO4 solution. So the first step here is write the chemical equation. You've got to have the equation. So here's the balanced chemical equation. And what do we see about their ratio? It's 1-to-2. So now we start with the volume of the acid, and we convert it to moles of acid using molarity of the acid. Then we go moles of acid to moles of base using the reaction coefficient, the 1-to-2 ratio. And then we convert from moles of base to molarity of the base using to volume of the base using molarity. So if we start with 25 milliliters, this is again using dimensional analysis. You can also use proportions for this. You've got three conversions. So the first conversion is converting between milliliters and moles using the molarity. And the second one is the reaction coefficient. Now you could have also written this here in liters, but the reason we chose milliliters is because we had milliliters there. And then you can use the molarity of the base to find the volume of the base. Again, the volume will be in milliliters in this case. So 158 milliliters. Cross out, cancel, 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 cancel. Okay, so this is how you could set it up. Again, you could also do three proportions. This would be proportion 1, this would be proportion 2, this would be proportion 3, and you can get the volume of the base. It's just like stoichiometry. So, another way of going about it, although this only works for special situations, is you take the molarity of the analyte times the volume of the analyte equals the molarity of the titrant times the volume of the titrant. Or, depending on what you have, molarity of the acid times volume of the acid equals molarity of the base times volume of the base, depending on how you set it up. It doesn't matter which is on which side, it's just a way of analyzing the information. This is a good equation. MA, VA, so molarity of the analyte, volume, molarity of the titrant, and the volume of the titrant. Now, this only works if it's a 1-to-1 ratio. So, if it's sodium hydroxide and hydrochloric acid, works great. In the last one, let's see, how would it work? So there's our equation. There's our M1V1 equals M2V2. 4.5, 25 equals 1.42 times volume of the titrant, 79.2 milliliters. However, that's not the right answer. Why doesn't it work? Because we've got 2 sodium hydroxides for every 1 sulfuric acids. So there's our correct answer. That is how to do it using this equation. So the trick is here, we've got the 4.5 molar sulfuric acid, 25 milliliters, and you put the 2 here on the side, the opposite side of what you're including the information in. So when you do a titration, the first thing we got to look at is the Buret, and this one here is a picture of the Buret with a little red top on it. Okay? There are 2 positions. On the bottom of the Buret, there's a stopcock. There's the open position or closed position. If it's open, volume of liquid will be running out. And depending on how you adjust it, you can disperse it drop by drop or a large amount at a time. So how to prepare a Buret. First, pour 15 milliliters of tap water into the Buret. Drain out as much water as possible into the waste beaker. Then put 50 milliliters of deionized water or distilled water into the Buret. Then drain out as much as possible. Then pour 5 milliliters of the titrant solution into the Buret. Drain out the titrant as much as possible into the waste beaker. Then fill the Buret with the titrant solution until the meniscus is just above the 0 milliliter mark. Slowly drain out the titrant until there are no bubbles in the nozzle. Here's a picture of a bubble in the nozzle. And you slowly can tap it as you are draining it out to try to get that bubble out. Be very careful of tapping it. This here is a picture of a meniscus. And the important thing to see in the meniscus here is this bottom of the meniscus is what you want to measure. So this is between 18 and 19. And to measure this precisely, you'd measure here, not up there. To measure it properly, you want to be at eye level with the meniscus, and you want to measure and line up with that meniscus. You can take it off of the Buret stand to do that, although you have to put it back on to measure that volume again. So this is how to read a Buret or a pipette volume. The volume here is going to be 23.45 milliliters. There's your 23, there's your 24. You're not going 4 to 25, so this is 23.4 here. And then this is 23.5, so it's in between those two. So this is the precision, and you estimate that last digit. What is being dropped out of the Buret is called an aliquot. Here is what phenolphthalein looks like at different pHs. So at a pH of 7, where it's neutral, it is clear. When it goes just past clear into the basic side, this is a base, it turns pink. You want it to be a very, very, very light pink at your endpoint. So here, this is a titration of a base with an acid using phenolphthalein indicator. So here you've got an acid being added to a base. So the indicator would start pink, and as you add more acid to it, it would get lighter, lighter, lighter until it reaches that endpoint. If it was clear, you had gone too far in that particular example. Tips. Always make sure every last drop of titrant reacts with the analyte before adding more. So wait and be patient. Wash reactions off the wall of the flask with distilled water. You spray it down so the reactants can go into the solution. Swirl it constantly. So these are some things you can do when you're doing a titration. Now I want to show you what a titration could look like with a smaller scale. So to do this, we're going to add a unknown sodium hydroxide into a container here. So this here is a small flask. We're going to add 20 drops of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20. So we have an unknown, and we'll write that down. We've got an unknown base. Okay? But we know we had 20 drops of it. And so now what we're going to do to it is we're going to add a single drop of phenolphthalein, which is an indicator. And in the presence of a base, you can see here that it's got a very pink color. We're going to place this on a white sheet of paper. So I'm going to place it on a white sheet of paper like this here, so I can clearly see the color. Then we're going to add hydrochloric acid to it. And let me see if I can adjust this so you can see this just a little bit better. So here you can see we've got our base solution, 20 drops of it that's unknown. And to it we're going to add an acid. Now the acid has to be a known concentration, so we're going to use 0.10 molar acid. And then we're going to count how many drops we get. And we want it to be the faintest pink we can. So we can add a single drop at a time of our acid. 1, and stir. 2, 3, 4, 5, 6, 7, stir, stir, stir. 8, 9, 10. 11, 12. That's starting to get clearer when I drop it in. 13, 14, 15. So in this titration, we were between 14 and 15 drops. So it looks like in the 15th drop, that's when it turned clear. So the best estimation on this one with a small scale is that I had 14 drops of acid to be at the equivalent point. So because I added sodium chloride and sodium hydroxide, and hydrochloric acid together, it's a 1-to-1 ratio. So that means I can use my M1V1 equals M2V2 equation. So here the molarity of the base is unknown, so that's molarity. The volume is 20 drops. The molarity of the acid is 0.10 molar, and the volume of the acid was 14 drops. So here we can solve for molarity, divide both sides by 20. So this here would be 0.10 times 14 divided by 20. So 0.1 times 14 divided by 20. And this gives us a concentration of the base at 0.07 molar. So our basic solution that was unknown had this concentration from our very quick and speedy titration. So tomorrow we're going to be using burets and Buret stands to find out more precisely the measurement of an unknown base, like this one here, that might have a different concentration. So that is our challenge. That's how to do a titration. See you later. Bye.